Hi all. Today we start discussing second module, that is the section 8, groups of permutations. In this session we discuss some groups, some interesting groups, which is non-abelian, finite, and some theorems related on these groups. Okay, so these are the examples of finite non-abelian groups. We might have seen some groups like G, L, N, or G, L, N, C. These are called general linear group over real numbers or complex numbers. These are in fact non-abelian groups, but it contains infinitely many elements. So these are the matrices. This consists of set of all matrices Aij, n by n matrices. These are the elements of M, N, C or M, N, R. M, N, R. These are set of all n by n matrices with the determinant not equal to 0. Det of Aij not equal to 0. So these are the non-abelian groups, but it contains infinitely many elements. But we start discussing finite non-abelian groups. Okay, that is permutation group. So that is nothing but functions. A permutation is a one-one onto function from a set to itself. Okay, onto itself. So we start with a set with consisting of three elements, 1, 2, 3, and you can consider functions from functions f from a one-one onto functions from a onto itself. Okay, so one such function is, if we consider 1, 2, 3 here and 1, 2, 3 here. So the trivial function is 1 goes to 1, 2 goes to 2, 3 and 3 goes to 3. So this is denoted by the symbol say f naught. This is a function from a to a, which is 1, 1 and 1, 2. So this is one such function. In a similar fashion, you can define another function from a to a. That is 1, 2, 3, and this is 1, 2, 3. And that is 1 goes to 2, 2 goes to 3 and 3 goes to 1. Okay, this is another function which is 1, 1 and 1, 2. So we call this function as some f1, and we have another function 1, 2, 3. This is 1, 2, 3 again, and we have f2, that is another function which maps 1 to this 3, 2 to 1 and 3 to this 2, and we have another one from a to a that consists of the mapping 1, 2, 3. 1 goes to this, another one is 1 goes to 2 and 2 goes to 1, and I'll map this as 1 goes to 1 first. Then we can interchange the images of 2 and 3 as 2 goes to 3 and 3 goes to 2. Similarly, you can construct two more. A to a, we have f4, 1, 2, 3. This is again 1, 2, 3, and here 1 and 3 are interchanged. 1 goes to 3 and 3 goes to 1, and 2 is fixed. The last one is denoted by f5, that is from a to a again, that maps this 1, 2, 3 to this 1, 2, 3 in the fashion 1 goes to 3 is fixed here, 1 goes to 2 and 2 goes to 1. So these are the 1, 1 onto functions from a to a. Since this a contains 3 elements, then there are exactly 6, that is 3 factorial functions, 1, 1 onto functions from this a to a. So if you denote these functions as a set, as f1, f0, f1, f2, f3, f4 and f5. These are the only 1, 1 onto functions from a onto itself. Okay, and we call this set as SA. Later we denote this as S3 since this A contains 3 elements. In general, we can denote it as SA. SA consists of set of all 1, 1, 1, 2 functions from A to itself. Okay, so in case of this A equal to 1, 2, 3, there are exactly 6 elements. So if we consider any, if you consider a binary operation on this SA as composition, if we consider F naught star or in general Fi star, Fj is operated as Fi composition Fj. Okay, so if we define composition as the binary operation on this SA, we can get this, since this Fi and Fj are 1, 1, 1, 2 functions or bijections, then this composition is also a bijection. So it should be an element of SA itself, because SA consists of all 1, 1, 1, 2 functions from A to A. Okay, so we can say that this star or composition is closed on this SA. Okay, or SA is closed under this composition, because a composition of any 2 elements of this SA is again in SA itself. Okay, so this SA along with this composition form a binary structure what we call groupoid or quasi-group. Okay, we have already discussed what is groupoid or quasi-group. And since this composition is associative, that is Fi composition, Fj composition, Fk, this can be associated in any manner. So we can get the associativity of here of these 3 elements as composition Fj, composition Fk. So this is in fact Fi of Fj of Fk. Okay. So this is this composition is associative here. So this structure can be considered as a semi-group as well. Okay, because this is a this composition is a binary operation which is associative, and we know that in any permutation group there exists this at least this element, because if you consider A and the trivial 1, 1, 1, 2 function is identity function f of x equal to x, or 1 goes to 1, 2 goes to 2 and 3 is mapped into 3 itself. Okay, so such functions are called identity functions. So if you consider any SA, this function f naught is always there, and this f naught can act as identity element. Okay, because Fi composition f naught will give Fi itself. Okay, this is because this is same as f naught composition Fi composition Fi. This is because if we have any x belongs to A, we can write Fi of f naught of x. This is Fi of x itself. Okay, because f naught of x equal to x itself. Okay, because of this reason we can consider this f naught as the identity element of this algebraic structure. So we can consider this SA along with the binary operation composition consists of this identity element f naught. So we can consider this as monoid. Okay, monoid. Finally, that means this proves the existence of identity element, and this is the associativity. Finally, we can say that if Fi belongs to SA, then Fi is a 1, 1 and 1, 2 function. Therefore, Fi inverse also exists in SA. Okay, Fi inverse is again a 1, 1 and 1, 2 function. So this belongs to SA. Okay, so because of this reason, we can say that this is an algebraic structure along with the existence of inverse elements. Okay, so each element of SA consists or possesses inverse of its inverse corresponding to that composition, because this is 1, 1 and 1, 2. So therefore we can consider this SA along with the composition is called, or this form, the structure of a group. Okay, for example, if you consider this F2, then what is the inverse of this? Okay, so inverse can be obtained from the rule that maps 3 goes to 1, 2 goes to 3, 1 goes to 2. Okay, 3 goes to 1. What is 3? What is 3 goes to 1? 3 goes to 1 is this one. 2 goes to here 2 goes to this is 3 goes to 1, and here 2 goes to 3, that is 2 goes to 3 here, and 1 goes to 2. So 1 goes to 2 is this. So if you consider the aroma, the assigning in the reverse order, you can get the inverse. So we can get F2 is the inverse of F2 is F1. Okay, so in order to get the inverse, you need to map is in the reverse order. Okay, so or you can say that F1 composition F2 will give the identity element. Okay, this F1 composition F2 of 1, how will you evaluate F1 composition F2 of 1? So this is in fact F1 of F2 of 1. Okay, so that is F1 of F2 of 1 is, here F2 of 1 is 3, therefore this is 3. Then what is F1 of 3? F1 of 3 is 1, so that will give 1. So we can say that F1 composition F2 of 1 is 1. In the similar fashion, you can get F1 composition F2 of 2, that can be from these two functions. 2 is mapped to 1 here, and that 1 is mapped to 2 again. Okay, so 2 is mapped to 2. And here, if you look into the image of 3 is mapped to 2, and here 2 is mapped to 3. So 3 is ultimately mapped to 3 itself. So if you replace this 1 by 2 and followed by 3, you can get this F1 composition F2 maps 1 to 1 and 2 goes to 2, 3 goes to 3. So that will give the identity element. So we can say that F1 composition F2 is in fact F0. Okay, so this proves that F2 is the inverse of F1, or F1 is the inverse of F2. Okay, so similarly you can evaluate all the inverses for elements of this SA. Okay, therefore this SA form a group along with the composition. But the interesting fact is that if we consider this F1 and F4, okay, or F3, if you consider F1 composition F3, what is F1 composition F3 of 1? How will you evaluate F1 composition F3 of 1? First of all, we have to evaluate F3 of 1. Okay, this is F3 of 1. F3 of 1 is 1, and that 1 is mapped to 2 here. So F1 composition F3 of 1 is F1 of F3 of 1. F3 of 1 is 1, so this is F1 of 1, and we know that F1 of 1, what is F1 of 1? F1 of 1 is 2, okay, so this is 2. But if you evaluate F3 composition F1 of 1, that is F3 of F1 of 1. What is F1 of 1? F1 of 1 is 2, then this is F3 of 2. What is F3 of 2? From this you can get F3 of 2 is, F3 of 2 is 3. Okay, so that will be 2 and 3. So from these two statements you can say that F1 composition F3 never be equal to F3 composition F1, which shows that in spite of getting the group structure here, which never be an abelian group or commutative group. Okay, so this is an example of non-abelian group. Since this contains exactly 6 elements, you can say that this is an example of finite non-abelian group. Now we can generalize this. If we have A is any set, let A be any set, then SA consists of set of all permutations denoted by some row. A row from A to A is a bijection. Row is a bijection. Then this SA along with composition operation is a group called permutation group. Permutation group. The elements of SA are called the permutation. That means a 1 1 onto function from A onto itself is called a permutation. Permutation is a bijection from a set onto itself. So the elements of this essay are called the permutation. That's why we call this group as permutation. Okay, so we can say that if A consists of n elements, if the cardinality of A is n, then SA is denoted by Sn. Okay, Sn. The cardinality of A, we use that number to denote this permutation group, that is Sn. Okay, so if A consists of only one element, if A is equal to 1 itself, then what is SA? Then we can say that there is only one function, one onto function from A to itself. Okay, so that consists of one element. So this is nothing but 1. This is that map. This is only function, only such function. Okay, and it is not customary to, or it is not easy to handle this symbol to denote the functions. So we denote the functions as this function as 1 mapped into 1. Okay, or in the previous case we have 6 permutations. So if we consider these permutations and we adopt a new notation to denote these functions. Okay, so to denote this function, we write the elements of the domain in the first row and we write the corresponding images under these elements of the domain. Okay, so here 1 is mapped into 1, so here we write 1 here and 2 here and 3 here. So this is in fact F0. Okay, F0 is denoted by this symbol. Similarly, how will you denote this F1? Okay, this F1 can be denoted by 1, 2, 3, and in F1 image of 1 is 2, so we can write 2 here, and image of 2 is 3, so we can write 3 here, and image of 3 is 1, then 1 here. So this is the notation for F1. In a similar fashion you can write F2, F3, F4, etc. So if we consider this A and SA, it consists of only one element. So we use the notation to denote this function as 1, 1. Since this consists of only one element, this is an abelian group. So and this is in fact denoted by S1. Okay, S1 is always abelian. Okay, S1 is always abelian because it consists of only one element. If A has two elements, then we can say that 2 factorial 1, 1 on 2 functions are there and it is denoted by S2. And how will you write that functions? This is 1, 2 and 1, 2. The only trivial function is identity function, and this is denoted by our F0. And we have 1, 2 here, 1, 2 here. 1 is mapped into 2 and 2 is mapped into 1, and this is our F1. So it consists of 2 elements. So the notation for this identity map is 1, 2, 1, 2. That is 1 is mapped into 2 and 2 is mapped into 2 itself. And the other element is F1, and it is denoted by 1, 2 and 2, 1. Okay, so this is an example of another group with the permutation composition or function composition, and we know that this contains only 2 elements. Therefore, if you write the group table of this, you can easily see that this group is abelian as well. So S2 is always abelian. Okay, and we have seen that S3 is not abelian. So S3 onwards we can get the non-abelian groups. Okay, so once you define Sn for n is equal to 1 and 2, those groups are abelian, and rest of the groups are, that is Sn from n equal to 3 onwards, those groups are examples of non-abelian finite groups. Okay, in general Sn contains exactly n factorial elements which is non-abelian, which is a non-abelian group. Okay, so in the next class we will discuss some the operations on this composition in Sn, and later on we will discuss some theorems or properties of this elements of SA as some theorems. Thank you.